Greetings to all. Today's section is on power spectral density function and cross spectral density functions. The statistical parameters like mean, variance, and most importantly autocorrelation functions are time-bound domain tools where in the study of random process we use these time domain tools. And now in this analysis of deterministic signals, equally important are frequency domain tools like Fourier series and Fourier transforms. So in this section we are going to discuss the frequency domain tools which are being developed for the study of random process. The definition of power spectral density. So consider a random process x of t and the power spectral density function S omega omega is defined as the Fourier transform of the autocorrelation, and it is given as Sxx omega minus infinity to plus infinity Rxx tau e raised to minus I omega tau d2. And the Fourier inverse transform of S will give you the autocorrelation function, and it is again defined as Rxx tau is 1 by 2 pi integral minus infinity to plus infinity Sxx e raised to I omega d omega. These equations are called the Wiener-Khinchin relations. So in the first case we get the power spectral density function of the random process x is denoted by S omega, and that is defined as the Fourier transform of autocorrelation function. When you take the inverse Fourier transform, we get back the autocorrelation function of the random process x of t. Now we are going to discuss some properties of this power spectral density function. So consider the random process x of t a continuous time WSS process, and some properties. The first one is the power spectral density function at frequency 0 is nothing but the area under the graph of the autocorrelation function Rxx. The second property, the power spectral density function is real and greater than or equal to 0. It is an even function. Then the average power of the process is defined as Ex squared of tau, which is Rxx at 0. This gives the average power of the process. The last property is, if x of t is again a WSS process, then the power spectral density function and autocorrelation function are Fourier cosine transform pair. So these are some of the properties of the power spectral density function which is applicable in the problems. Next we move on to noise. So here you consider any physical domain, we have unwanted persistent fluctuations in the systems which is due to random process, and this is practically called the noise. So for example you can say the irregular fluctuations of an electrical transmitted signal, so that gives you noise. So what is a noise in random process? So a white noise random process is W of t. It is a white noise process if the following conditions are true, if and only if. First condition is the mean of this process expectation of W, that is 0. The second one is the process has an autocorrelation function and it is equal to 1 by 2 n naught into delta of tau. where n naught is greater than 0 and delta tau is an impulse delta function or called Dirac delta function. This Dirac delta function is denoted as h epsilon tau. Dirac delta function. It is denoted as delta tau, and the so here you consider the function h epsilon t, which is defined as 1 by epsilon for between a minus epsilon by 2, a plus epsilon by 2, 0 elsewhere. So here we see, consider this graph where I have the width of a rectangle and I give the height as 1 by epsilon. Here you see this h epsilon of t is defined with height 1 by epsilon, and the width of this rectangle is a minus epsilon by 2 a plus 2a plus epsilon by 2. So the width is nothing but epsilon, epsilon greater than 0, a is some real number, and the area is of this rectangle is 1 unit. This is called the Dirac delta function, and it is defined as delta t minus a is equal to limit epsilon tends to 0. H epsilon of t. The meaning is when epsilon tends to 0, what happens here? The height is considerably infinite, and what happens to this width? It is infinitesimally small, but the area is always 1. This function is called the Dirac delta function at a. So with the property integral minus infinity to plus infinity h epsilon tau, which is equal to integral minus infinity to plus infinity. You know what is h epsilon of t? 1 by epsilon dt. That is equal to 1. So this is the concept of Dirac delta function. So this notation h epsilon of tau, when limit epsilon tends to 0, that leads to this delta function at a. It is called the Dirac delta function at a. It has some properties which we are going to discuss now. Some properties of the delta function. The first one, you see that delta t minus a is infinity at a, t equal to a. At all other points where t is not equal to a, the delta function is 0. Next is the integral minus infinity to plus infinity delta function, there is 1. That is, as I told you, the total area of that function is 1. And the third one is integral minus infinity to plus infinity delta t minus a into f of t. It is nothing but the function at a. Moreover, we can see that in the second and third properties, if there is a change in the integral, the limits, that is if it is from a minus epsilon to a plus epsilon, this property remains the same. So, in fact that we know that h epsilon t denotes the area of the rectangle, and that area is nothing but 1 unit. So, it remains the same. Next we see the property of cross spectral density function. See here we consider two random process x of t and y of t. What is the cross power spectral density function? That is denoted as s x y omega, and it has the following properties. S x y omega is the same as S y x at minus omega. The second property, S x y of minus omega is S star x y of omega, where S star is nothing but the complex conjugate. And the third property, if the two random processes are orthogonal, then the cross spectral density function S x y is equal to 0. So, here the three properties are again going to be applicable in the problems which we are going to discuss. And here, unlike the power spectral density function S x x, the cross power spectral density function S x y is a complex valued function. The following table gives some Fourier transforms of functions and its inverse Fourier transforms. These are applicable in the problems which are to be discussed. So, you see Sx, this is a Fourier transform of the autocorrelation function. And you see Rx, it's the inverse Fourier transform of the power spectral density function. So, by definition, it is defined in this manner. Power spectral density function is nothing but Fourier transform of autocorrelation, and its inverse transforms gets back to the autocorrelation function. So, here we have the inverse transforms of the functions and the Fourier transforms. These are some of the functions where the Fourier transform and its inverse transforms are given. Yeah. Now we will discuss some problems relating to power spectral density function and finding the PSD. The first one, here to find the power spectral density of a WSS, wide sense stationary random process with autocorrelation given by R2 is equal to e raised to minus alpha tau squared, where alpha is a constant. Okay, so here we have the autocorrelation is given and we are supposed to find the power spectral density function. So, the solution to this So you know by the definition that the PSD is defined as integral minus infinity to plus infinity autocorrelation e raised to minus I omega tau d tau. Here we know that this is the R of t process is given as e raised to minus alpha tau squared e raised to minus I omega tau d tau, which is nothing but minus infinity to plus infinity e raised to minus alpha tau squared plus I omega tau d tau. This is equal to, by completion of squares, we will get I, this is I. I omega tau minus I omega square by 4 alpha plus I omega squared by 4 alpha d tau. So this is equal to e raised to, you see that here it will be, you can remove this out. So in this case we will have e raised to I omega squared by 4 alpha integral minus infinity to plus infinity e raised to, this will reduce to root alpha tau plus I omega by 2 root alpha the whole squared d tau. So once we have so in this case we will continue. So it is equal to e raised to minus omega squared by 4 alpha integral minus infinity to plus infinity e raised to minus alpha root alpha tau plus I omega by 2 root alpha the whole squared d tau. Next, substitute u as root alpha tau plus I omega by 2 root alpha. Implies du is nothing but alpha root alpha d tau, which implies d tau is nothing but du by root alpha. Therefore, our equation becomes, call this as equation 1, substitute in 1. So we have S W is equal to e raised to minus omega squared by 4 alpha into minus infinity to plus infinity e raised to minus u squared d tau, you can substitute this du by root alpha. We see that this integrand is an even function, therefore it becomes e raised to minus omega squared by 4 alpha by root alpha 0 to infinity 2 times e raised to minus u squared du. So again we call this as equation 2, make a substitution. Substitute v is equal to u squared, and from this you can find out what is dv. Tu du implies du is equal to dv by 2u. U is nothing but root v. Therefore, we will substitute this in equation 2. So substituting in the equation 2, we will see we have s omega is equal to e raised to minus omega squared by 4 alpha integral 2 times, yes, 0 to infinity e raised to minus v dv by 2 root v by root alpha. This root alpha is also there, and then we can, by simplification, this you know that it resembles the gamma function 0 to infinity e raised to minus v raised to minus half dv, which is the same as omega squared by 4 alpha by root alpha. This I am going to simplify it further. E raised to minus v raised to, it is 1 by 2 minus 1 dv, and this will give you minus by root alpha into gamma of half. Gamma function, when gamma of half, you know, it is root pi, therefore it is so this is the power spectral density function for the given autocorrelation function. And this is the first problem. Next problem we will discuss the autocorrelation function will be given. We will find out what is the power spectral density function. The power spectral density function PSD of a WSS process of a WSS random process is given by S of W equal to 1 and 0. 1 when mod W is less than W naught, 0 elsewhere. Here we have to find the power of the process, of the random process. So you know what is the power of the random process? It is the autocorrelation at 0. So basically we find the autocorrelation function, and then at 0 we will get the power of the random process. So the solution to this is the By definition, you know autocorrelation R2 is 1 by 2 pi integral S omega e raised to I omega to d2. Here 1 by 2 pi, the function, power spectral density function is 1 at between minus W naught to plus W naught. So we have the limits as to plus W naught 1 into I omega to d2. So this, you know, by integration we have this is between minus omega naught to plus omega. This is 1 by 2 pi e raised to I omega naught to minus lower limit I minus I omega naught to whole divided by I omega. Substituting the limits we have, so it is 1 by 2 pi I omega naught, and you know that e raised to, it is of the form e raised to I theta minus e raised to minus I theta. So in this case you will get 2 times I sine the angle omega naught 2. So after cancellation you will get sine omega naught 2, that is the angle, divided by pi omega naught. This is the autocorrelation of that function. Now the question is about to determine the power of this random process. So the power of a random process is nothing but the autocorrelation function at 0. So what happens when I substitute to find the we will do it again. Okay. To find the power, it is nothing but R at 0, which is equal to, now tau takes the value 0. So it is nothing but 0. So the power of this random process is 0. So we'll discuss one more problem. Consider the autocorrelation function. Okay. Function of a WSS, wide sense stationary random process, is given as R of tau alpha squared e raised to minus 2 lambda mod tau, absolute value. Here the question is to determine the power spectral density of this function. So here again you know that power spectral density of this function S omega, it is defined as minus infinity to plus infinity R tau e raised to minus I omega tau d tau. Substitute your autocorrelation function, which is nothing but minus infinity to plus infinity alpha squared e raised to minus 2 lambda absolute value tau d2. This is equal to alpha squared, and since you know the mod value takes, it is defined as minus 2 less than 0, 2 when 2 greater than 0. So we split this integral between minus infinity to 0. It takes the value, here I will write this, okay, e raised to minus 2 lambda. Here the first one, less than 0, it takes the value minus 2. So it is minus into minus plus 2 into e raised to minus I omega 2 d2 plus the second integral, it is from 0 to infinity. Again it is e raised to minus 2 lambda modulus of t, when t greater than 0 is nothing but 2 itself. So it is minus 2 lambda 2 e raised to minus I omega 2 d2. So here we have alpha squared is common, you can remove it out. So minus infinity to 0, it is 2 times 2 lambda minus I omega d2 plus integral 0 to infinity e raised to minus 2 lambda plus I omega d2. So this is equal to alpha squared minus infinity to 0 e raised to 2 into 2 lambda minus I omega d2 plus 0 to infinity e raised to minus 2 lambda plus I omega d2. So this is equal to e raised to 2 lambda minus I omega by 2 lambda minus I omega plus e raised to minus 2 lambda, there's a 2 here, 2 lambda plus I omega 2 by minus 2 lambda plus I omega. So this limit is between minus infinity to 0. Similarly here you will have it between 0 to infinity. So you substitute the limits now. So the lower limit, you know, it is going to be 0. So we have the upper limit, that is 1 by 2 lambda minus I omega plus, again here the upper limit is going to be 0. We have the lower limit, so minus into minus you will get plus 1 by 2 lambda plus I omega. This on simplification so this is the autocorrelation function. When given the autocorrelation function, we found out the power spectral density function, yes, omega. It's a function in omega. So in this section now we discussed autocorrelation. With autocorrelation function we found out the power spectral density function of a random process, and also when two random processes are given, the cross power spectral density function was also explained by the frequency tool. The tool which we used was Fourier transforms. Thank you.